of Lab 3 magnetic field of a bar magnet. The purpose is to investigate the distance dependent of a magnetic field of a small bar magnet, measure the magnetic field of the magnet on axis using a Biot-Savart Law for magnetic fields, and simulate the magnetic field of a bar magnet using Python, and then finally compare the measured magnetic fields to the simulated magnetic fields. And the preview of the findings is shown below. The fundamental principle used is the Biot-Savart Law, which relates the magnetic field produced by an object at an observation point to the current running through the object and the distance between the source of the field and the observation point. The magnetic field dB for a section dl is the following, and then more formulas related to this law are shown on the screen. As we discussed in the introduction, the main physics idea is Biot-Savart Law. Below are more figures that relate to this idea. Some assumptions we made are that the bar magnet has a magnetic dipole moment. This magnetic dipole moment vector is in the same direction as the magnetic field. The only recorded magnetic field via the magnetometer were that of the Earth and of the bar magnet itself. The reasoning for the models is that the bar's magnetic field usually matches that of a magnetic dipole, so this reasoning was kept in mind while creating the models. The system was the observation point, the magnetometer, and the surroundings was the bar magnet, which was producing the magnetic field. The initial conditions was the bar magnet placed at the end of a meter stick with the magnetometer app open on the phone. The materials needed for this experiment was a bar magnet, magnetometer, meter stick, and tape. The procedures for this experiment are shown below. Some observations we made was when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. On the left are shown formulas used for the calculations in this experiment, and then on the right are the values we got using these formulas. This part of the code shows a physical constant which is 1e-7, the creation of the magnet at the origin, and the creation of a function for the magnetic field. This part of the code focuses on the arrows created by the code. We scale the arrows, determine how far away from the origin they will be placed, and determine the observation location. This part of the code also helps with the location of the arrows and the overall visualization of the magnetic field. When comparing the data and model predictions, we can see the arrows point in the same direction. Some explanations for errors are that other sources of magnetic fields could be distorting the measurements, such as electronic devices. There could also be inconsistent placement of the phone, such as slight movements of the phone during measurements. This would lead to inconsistencies in magnetic field measurements. If the surface was not completely flat, this would also interfere with the distance measurements and the magnetic field measurements. And there could also be a measurement error when determining distance between the magnetometer and the magnet. The measured magnetic field would be different due to not accounting for the magnetic north. The x components would be different because magnetic north would contribute to the magnetic field measurements. The y components would also be different due to not accounting for magnetic north. And then at an intermediate angle, the magnetic north would contribute to both the x and y components of the magnetic field. Because we lay the magnetometer on a flat surface, the z component would not change or see any negligible changes. And then for the answer to this last question is the magnitude of the magnetic field would increase due to the combined magnetic fields from two magnets. We would expect the magnitude for the new magnetic field to be approximately double the magnetic field of one magnet. The measured distances for each magnetic field would decrease due to the increased magnetic field magnitude from the two magnets.